Okay, this is problem 4-ish in the practice exam, which says, suppose I have a matrix A with 4 times A101 is 3 times A123, and I'm supposed to find a vector x with AX equals 0, and it probably also says with x not 0. Okay, so the reason why does it say with x not 0?
That'd be too easy.
Yeah, good. Because matrices all take 0 to 0, right? As functions, that is a absolute dead given. They have to. So, why do they have to?
Don't want to take 0 with anything else.
I mean, that's fair. It would be rude to take 0 somewhere else where it's not used to it. But why do they take, like, why
It
is...
would be fucking weird to get information out of the lack of information.
Yeah, but, like, functions take 0 elsewhere all the time, right? Like, you have a line, y equals 3x plus 2, right?
Because
it takes 0 to 2.
Matrix ops is a series of dot products.
Okay, yeah. So one way we could think about it is there's all these dot products. Another thing we could draw upon is that it's a linear operator, right? So when I'm thinking about A times, like, say, CX, right? This is the same thing as C times AX. You guys with me on that? Okay, and if I replace x with the 0 vector, then this, well, C times the 0 vector is still the 0 vector, right? So this means that A done to the 0 vector has to be C times A done to the 0 vector for all constants C. You guys see that? So this is like x equals AX for all A's. Right, and so like has to be x, and also has to be twice it, and also has to be 17 times it.
Okay, and like 0.
And the only way that's going to be
dimensional. There's no direction. Like it's sick.
So this is going to work. Like this is going to force, right? The fact that this works for all C's is going to force A of the 0 vector to be the 0 vector. So it's kind of linearity, and the fact that this is because linearity makes me think that maybe this is something to do with linearity. You see that? So I'm going to manipulate that thing a little bit. I'm first going to try to get the A's together. So I'm going to get this stuff to that side. So I'm going to say this is 4A101 minus 3A123 is 0. Vector? How was I allowed to do that operation? What category of thing is this? Like this is me doing subtract 3A times 123 to both sides. How is that valid math? Like, this is going to be A times a vector. What kind of thing is A times a vector?
Another vector?
Yeah, it's another vector. I don't know how big it is because they didn't tell me what size matrix A is, but it's some other vector. What's 3 times another vector? Still a vector? So I'm subtracting a vector from both sides?
Yeah.
That's okay. I'm allowed to do that. Right? Really, I'm adding -1 times the vector to both sides of the equation. Vector addition works so that they'll cancel out on the right. And on the left, I'll get this. This is vector addition going on in the middle here. So now I'm going to use my properties of matrices, right? So I'm going to use the scalar transition. So I'm going to use linearity to pull the scalars inside. So I'm going to say that this is A times 404
Oh, that's 1, 0, 1.
plus 3, oops, not 3, plus a times, and then here I'm going to put
Negative 3,
-3, -6, -9. And this is still going to give me the 0 vector, right? And then I'm going to say, oh,
Could you factor
well, say that again.
Could you factor out an A?
Yeah, can you factor out an a?
Oh.
It's a function, dude.
yeah.
Like, if I had f of x plus g of x, right? You wouldn't be like,
Well, they're the same,
Yeah, it's the same function though.
just different, different things.
Yeah,
inside
so
the
it's just
argument.
2f of x. Oh! Oh!
yeah. So it's not factoring that you're doing here. It's exploiting linearity. Does
Okay.
that make sense? So here I'm saying I have a times a vector plus a times another vector.
Yeah.
And I'm saying, okay, well, A is a linear operator, right? So I have this, I have AX plus Y is AX plus AY,
That's what we did in class, yeah. Okay.
right?
Yeah.
That's linearity. So I'm going to exploit that here, which is factoring a matrix.
That's what it feels like though. If you think
It is too. The thing is that the fact that matrices are linear means that you can factor matrices.
Okay.
So yeah, it's matrix factoring.
So if you
So you get A, and A is going to be done to 404 plus -3, -6, -9. And this is going to equal the 0 vector. And then this is just vector addition going on in the middle.
Yeah.
So that's going to be A times the vector, let's see, what do you get?
1, -6, -5.
Cool.
Oh, that's our x.
Yeah.
There's your vector.
Oh.
Does that make sense?
Yeah, I guess I was overcomplicating it in my head.
Yeah, this one's really easy to overcomplicate because it really does boil down to like, dude, matrices, linear, you can factor.
Goes back to the linear operator thing. Knowing when to treat it. I mean, it's always a linear operator, but
Yeah, knowing when to exploit linearity
Yeah.
can be a thing that you have to get used to. On this, the real trick is this, like, you can subtract this to the other side and then you can factor an A out is a big deal. Another way you could approach this problem is you could say A done to 404 gives you the same thing as A done to -3, -6, -9. +3, +6, +9 rather.
oh yeah,
You
yeah.
guys
Yeah.
see that?
Yep.
And that really amounts to AX equals AY. And then you could subtract it.
It's simple.
Same deal. Does that make sense?
Yeah.
I'm not really, I guess I said another approach, and this is
This-
not really the only difference is that
You
on the
started
other
off-
one I subtracted first,
And then you went with the A.
and then pulled the scalars in, and on that one I'm pulling the scalars in and then subtracting. Cool. We'll end up asking questions a lot about these, because one kind of criteria for this is like, if I know this happens, this matrix A is in 1-to-1. You see that? Is not 1-to-1. I know for a fact now, after I got to this, I know that the matrix A is singular.
Yeah.
The reason I know it's singular is that it takes this thing to 0,
Yeah.
and it also takes
Oh, yeah.
0 to 0.
Oh, that's cool.
Right, so as soon as you can demonstrate that it has something that's not 0 that goes to 0,
Yeah.
really cool thing, then it must have infinitely many things that aren't 0 that go to 0.
It's so sick.
where are the rest? So there's 1. What if I ask for 3?
I would. See, how would I approach that? I would. So if it's singular, that means that the columns are linearly dependent, which means that I could like parameterize the one which represents the other, and then like plug in any value for like that thing, and then it would like. Yeah.
Sure, but also you.
Hmm?
Sure. That'll work. It's deeper than you need to go. If I wanted another vector that goes to 0,
You just multiply it by both sides by some arbitrary scalar.
yeah.
Oh,
So
yes.
if this thing goes to 0, then twice this thing also goes to 0. Because I can pull the 2 in there, and the 2's going to get absorbed into the 0.
Yeah. Okay. And same thing with any constancy.
So yeah, once you have one vector that goes to 0,
You know that all.
you have infinitely many. Any scalar times that vector also goes to 0.
And if
Oh,
it
yeah, that
wasn't
makes
that vector, then
Say again?
if it wasn't that vector, though.
I don't know. I don't know what this thing does to anything that's other than this vector, actually.
Okay.
Like, really, the bottom line of this is that this statement really boils down to knowing that fact and basically nothing else.
Alrighty.
If you knew that you had 2 that went to 0, you could know that their sum also goes to 0.
Well, that's what we're doing. The above step.
Kinda, yeah.
Yeah.
But I mean that if you had 2, like, say, totally different vectors,
Oh.
like if you knew, for instance, that a times x was 0, and also knew that a times y was 0, then you would automatically know that any vector a times like cx plus dy also goes to 0.
Okay.
Does that make sense?
Yeah.
Linearity would give you this pretty fast.
Mhm.